right. Let's see if I'm running. It looks like I might just be. Welcome, ladies and gentlemen, to my online and my online office hours here. My name is Dr. Sean Clovell. I am the professor of anatomy and physiology at Arizona Western College, and this is week 3 of the spring semester 2024. As I open up my Canvas here, this is my announcements for my online class as well as my in-person class. And so I just want to kind of get some of the housekeeping items out of the way, and then we'll get into some real kind of more course material, some substantive material as well. Let me get a big drink of water and we will go. All right. So, again, this is your Canvas. I'll give it the student view. Your Canvas lives in the modules. So go ahead and check out, look at the syllabus. That's why it's there the first time you go in the online schedule, particularly, and we'll look at the online schedule. But as we take a look here into the cellular level of organization, don't show there. The cellular level of organization, I can unmerge that. All right. As well as we progress through the chemical level, so we've finished, hopefully getting past that chapter 2 material. My computer's acting a little slow. I apologize there. There we go. But the idea is that this chapter 2 and 3 test, we'll call it test/exam, will be completed, or will open here on February the 8th. So a week from tomorrow, we'll get into, again, chapters 2 and chapter 3. We may not even start histology here until after our chapter 3 exam. But we'll have that there opening up a week from tomorrow, February the 8th, chapters 2 and 3, the chemical level of organization as well as the cellular level of organization. And so let's take a look here on our Canvas on the modules here. So on the modules, you'll see that chapter 2 has a couple of introductory videos. It has, you know what? I didn't even check if my mic was. Yeah, we're good. It has a couple of introductory videos. It has the, what is this? The chapter itself, the textbook chapter here. So it's in a PDF format. If it'll take up here, you can see there's the chapter 2. Chapter 2 is the chemical level of organization. Chapter 2 is broken up into 3 major parts, right? Excuse me, 3 major parts. 6 or 7 major parts. You'll see that there's the intro to chemistry, kind of the most common elements of the body, atomic structure, atoms and elements, chemical bonds, chemical reactions, and then I'm cutting up today those last 2 portions, so take a look. Remember to come back here because inorganic and organic compounds will be published here tonight after these announcements here. It was brought to my attention. I got to finish it and post, and I'll post that here very briefly, shortly. Oh, sorry, that was chapter 2. And chapter 3 is progressed just the same way there. So if we go to modules, just below chapter 3 is the chapter 2 material. It includes an introduction to cell biology. So if you took 181, this is very similar to the material that we see in the beginning of 181 or throughout 181, cell biology. So there's the chapter again, as you can see here, as it relates to specifically the parts of a cell. And then chapter 8 here, the cellular level of organization, including the cell membrane, cytoplasm and organelles, DNA and DNA replication, protein synthesis, cell growth and division, as well as cell differentiation. Cell differentiation is the concept of how cells, which start from a very common lineage, right? We all start from one fertilized egg, but then all the tissues in our body come from one of these 4 different types of stem cells. And so the specialization, so even the skin cells, how they specialize from the skin or hair or nails, they all derive from the same stem cells. And so the differentiation is the specialization, might be a term that we use as it relates to the cells. And so we've got chapter 3.7 there being that concept of cell differentiation. So again, there it is, chapters 2 and 3, the cellular level of organization. That one's coming up here on the 8th of February, where we're looking at chapters 2 and 3. The laboratory material here, we kind of slowed down as it relates to my online class. They had like 5 lab assignments because their online lab kit requires a lab inventory as well as a safety review. So they flew through 5 labs, and congrats on them for that. But now they have a single lab here related to introductory to the microscope. So microscope as it relates to anatomy and physiology. And so that's the lab assignment number 6 for those students there that are taking my online course. The other component here, and I should probably add it to the modules, so I'll add it to the bottom of the modules so you can get to that. But there is a extra credit assignment here, so I've published an extra credit assignment. This relates to probably one of my last housekeeping items, unless something else comes up. But it is the PBS special Beyond the Elements. So if you watch the series Nova, this is a special derived by Nova. It's really loud in my headphones, and you probably can't hear anything. So I had to turn that down real fast. But again, what you'll see here is a extra credit video here. You'll see that some questions will be pop up as the video plays. You'll be asked to answer those questions, and then once it's completed, I'll confirm the extra credit. So it'll probably say 0 out of 0 to start after you completed this. I should be mindful that you'll have as much time as you need, so you can pause it, you can come back to this video. It has no real restrictions in terms of its use. You can complete this at your leisure over the next, I think it's a week, the next week or so. And so I think it'll be a fun way for us to kind of review the chemistry of biology, or the chemistry of human life. So that is under assignments. I might as well just drop it for my online class and make sure that it sits under the modules as well, because I do want my class to be really focused on the modules. I have to leave my student view. All right, and so let's put it right there. Oh, it is. It already was there, huh? Oh, apologize for that. Let me just delete it. It was there. Sorry. It was underneath lab material. It's kind of where I should have addressed it. It's right there. Extra credit beyond the elements, chemistry of life underneath the lab treatments. As you can see, it'll be worth 0 points when you see it on your grade sheet. It may say 0 out of 0, and then I'll apply those points at the appropriate date, probably after the due date, shortly after the due date. Okay. So, as it relates to, let's kind of cut a topic here. So, let me just open up my slides here, and while I have the opportunity here to record chapter 2.7 inorganic molecules, kind of review that with the class that I have. Pull up my slides here. You guys are like straight up watching the magic happen in place. It's like the background of my lectures here. Let's see. I'm going to start from I think I have chemical reactions. So I won't record chemical reactions. Maybe I will record chemical reactions. Let's see. Now let me start with the stuff that you guys don't have. Chemical reactions was where we end, so we'll call it 2.7. And we're going to hit off with inorganic molecules. Or inorganic compounds, excuse me there. So hit that slide there. And so inorganic compounds essential to human functioning. We're really going to talk about water being the first component there. So water and water's special properties, as well as some acids, bases, and salts. All right. Let me do one thing here. Where's my over? There it is. All right, welcome to Anatomy and Physiology at Arizona Western College. I'm your professor, Dr. Sean Clavel. Today we're going to talk about inorganic compounds that are essential to human functioning particularly. And when we think about the concept of inorganic compounds, remember that we're talking about a substance that does not contain both, jumped too fast. A substance that does not contain both carbon and hydrogen. So you can see water here is one of the most common inorganic compounds. It derives close to 2/3 of our body by weight. It contains hydrogen, however, there's no carbon there, and as a result, it's an inorganic compound. Organic compounds, those are basically carbohydrates, proteins, nucleic acids, and fats. Lipids is also a reference there. And so a few examples of inorganic compounds include water, hydrochloric acid, like it's found in the stomach, produced by your stomach, and carbon dioxide, which is an example of a inorganic compound that contains carbon atoms but no hydrogen. Now let's talk a little bit more about water specifically. It's the most important constituent of the body. It accounts for about 2/3 of the body by weight. And water has a few unique properties that allow it to be so vital to life. And so we're going to go through that list here. The first is that what we may refer to as its compatibility with life, meaning water is the only substance that occurs as a solid, ice, a liquid, water, and a gas at temperatures that are compatible with life. So the first unique quality of water is its compatibility with life, its ability to be in all three of its states at a temperature compatible with life. Now, the next one here is called polarity. Polarity is the concept here that there's a, gotta get my pen out there, that there's a slight negative charge here on the oxygen. There's a slight positive charge here on the hydrogen. And so it's, again, the hydrogen bond has a small positive charge. Where's the oxygen? Well, yeah, it has and it's binding to the slight negative charge on the oxygen here. So these weak bonds are of hydrogen bonds. Allow for two properties of water there: the ability for it to exhibit cohesion, and cohesion is its ability to stick to other water molecules. And then adhesion, the ability for water to stick to other polar molecules. And so probably the best phenomenon relating to that is that of surface tension. The ability for objects like boats, which have a greater surface area than its density, to float on water, as well as some other insects. And so the concept of its polarity is that we have a positive end, a slight positive end, which is the hydrogen portion, a slight negative end, which is the oxygen portion. And so those opposites attract, and we have these weak hydrogen bonds that happen across, a great in vast quantity over a small drop of water. To go with this concept of polarity, water is also what's maybe referred to as the universal solvent. So if a solute is, for example, like salt or sugar, that's the actual substance that's being dissolved in the solvent, which is water. And ultimately, the result of that mixture between a solute and a solvent is what we may refer to as a solution. And so because of that polarity of water, let's take table salt for an example. Because of water's polarity, you can see that there's a slight negative portion of the oxygen that is encompassing the sodium ion, right? So the positive sodium ion here is fully encompassed by the negative portions of the water molecules, the oxygen portions here, whereas the chloride ion, the negatively charged chloride ion, is surrounded by the positive portions of the hydrogen ion of the water molecule. And so far we've talked about the compatibility with life, water's polarity, as well. Going with water's polarity is its ability to be that universal solvent. Here's a slide for you here, right? The polar charges of water molecules allow water to disrupt the ionic bonds, just like we saw with that salt, and dissolve a number of those other inorganic molecules. microphone up a little bit. Maybe I'm not blasting you out. And so our bodies even contain many dissolved elements. So water is generally considered to be that universal solvent. Water provides an effective lubrication. So, because there is little friction between water molecules, even a thin layer of water can greatly reduce friction between two moving items, two moving structures. So the example here is the synovial fluid of your joints, which is a thin lining of aqueous fluid, so water-based fluid. It's almost the consistency of like an egg white, a raw egg white, and it sits between the joints of the body, the movable joints of the body. So in between your knees, there is this kind of egg white consistency fluid called synovial fluid. It actually decreases. It provides a frictionless environment for your knee, for example, to slide and glide as you bend and extend your knee. So water is the predominant content of synovial fluid. It's a predominantly water, as well as some other glycoproteins, glucose and protein, and it provides a lubrication and a frictionless environment for your knee to bend. And then finally, water demonstrates a high heat capacity. This is the ability to absorb and retain heat. So water has this high heat capacity because those molecules are attracted to one another through those hydrogen bondings, and it's going to take a lot of energy to break each of those bonds. To break each of those bonds. To break those bonds in total, in sum. And so that transition from liquid to vapor demands significant energy, and a lot of that heat is ultimately carried away when it finally does change from a liquid to a gas. And so that is the concept of perspiration and thermoregulation. So when you sweat, that water absorbs that heat, has a high thermal inertia, meaning it can it changes temperature very slowly. And even for that water, that perspiration to evaporate requires that absorbs a lot of heat as well. So the ability to retain heat, to absorb and retain heat. The next thing we're going to talk about is the pH scale. And so the pH scale was developed by a Danish biochemist and brewer by the name of Søren Sørensen in 1909. And what he found by trying to maintain the ultimate environment for his bacteria to live was that he could measure the acidity of a substance based on the amount of hydrogen ions present. And so ultimately, hydrogen ion, I might just kind of put this here. You'll see this. Let me get the pen there. You'll see this in a lot of research, but a hydrogen ion is simply just a proton. So it's called a proton. So a hydrogen ion is just a proton. You can imagine there's a proton in the middle here, and it has lost its electron. So you put that little negative there. It has lost its electron. So as a result, it's simply just a proton, right? So a hydrogen ion is simply just a proton. So the amount of protons in a substance kind of helps us to determine its acidity or its pH. Now, let's talk a little bit about this pH scale. So, the first one that we'll talk about is acids. Acids are referred to as biological compounds that release hydrogen ions, as we mentioned, protons when they're placed in a solution. So, a acid is often referred to as a proton donor. Hydrochloric acid. Hydrochloric acid is an important example of an acid in our stomachs, and it's necessary for the digestion of certain foods. So hydrochloric acid is HCl. It yields hydrogen and the chloride ion in a solution. Ultimately, acids have a low pH on the pH scale, somewhere between 1 and 6.9. And the more hydrogen ions released by a substance, the more acidity, the more acidic it becomes, the closer to 1. These are, again, proton donors. Bases are biological compounds that release hydroxide ions, when placed in a solution. This is also referred to as alkalinity. Bases have a high pH on the pH scale. It goes from 7.1 to 14, so the scale goes from 0 to 14. The more hydroxide ions released in the solution, the more alkaline the substance is, the closer to 14 it is. Bases are essentially referred to as proton acceptors. And so if we take a look here, what we're referring to is kind of the chemical equation of, okay, if it has a lot of hydrogen ions, right, it's acidic. If it has a lot of hydroxide ions, it is alkaline. And ultimately, what we get is this equation that comes out to water. Right? So in equal parts, what you have is ultimately water, but hydroxide ions increase. When hydrogen ions increase, this is acidic. When the hydroxide ions increase, it is alkaline. And so kind of this reference here helps us to discover that water, or distilled water specifically, which is an important pH regulator, is a compound that is a neutral, right? Or a neutral is a biological compound that releases both or equal hydrogen ions and hydroxide ions when placed in a solution. So water is an example. The dissociation of water produces a hydrogen ion and a hydroxide ion, and it's important that the body is able to maintain an appropriate pH because that contributes to the efficiency of chemical reactions. You'll see here in our organic molecules section where we see that water can, because of the We'll see that water can actually, acidity can denature our proteins. It can actually disrupt proteins, and so the denaturation or the breaking up of particular organic compounds, particularly a protein, which is responsible for a lot of the chemical reactions that occur, catalyzing chemical reactions that occur in the body. Once they're altered by temperature and acidity, they don't function anymore. So chemical reactions in the body can start to slow down and even stop if the body becomes too acidic and even too alkaline. Now, a buffer is a substance that can resist changes in pH, and we have buffers in our body fluids that release hydrogen ions when the pH begins to rise and become more basic, and they can also take hydrogen ions out of a solution when the pH begins to fall. So buffers are substances that can absorb or liberate hydrogen ions to maintain a constant pH and resist changes in pH. Many buffers are made by adding a weak acid with the salt of that acid. All of our body fluids contain buffers. Carbonic acid is a weak acid, and the salt is a buffer. Sodium bicarbonate is another example of a buffer. The last reference here, or definition we should identify here, is we talked about some acids, some bases, and now we should include a salt, which is an electrolyte. And so that might be a new term here, but basically as an electrolyte is a any molecule or any atom that has a charge, right? So the sodium ion has a charge, that is an electrolyte. Potassium has, when it has a charge, it has a positive charge, that is an electrolyte. Calcium, let me give you a couple examples here. Let's pop them on the screen here. Oops, sorry. So some of the most important electrolytes in the body here include like potassium, calcium, sodium, right? These are electrolytes. As well, chloride, phosphate. So anything that has a charge, right, when in abundance has a charge, is referred to as an electrolyte. And ultimately, this charge helps us to maintain the cell membranes of the muscles and nerves that allow signals to conduct across them. But a salt is an electrolyte that releases cations other than hydrogen. So example here is table salt, right? Sodium chloride. It releases the sodium ion, which is positively charged, a cation. It releases a chloride ion, which is the negatively charged anion. And because you don't get because you don't get hydrogen ions nor hydroxide ions, the result cannot be measured. The solution cannot be measured on the pH scale. So to wrap up the chapter here, as we talked about some inorganic molecules or compounds, the most important being water. Its unique characteristics that include the compatibility with life, its polarity, which allows it to become the universal solvent. It provides lubrication to areas of the body that have friction, like the joints of our knees. And water also has the ability to absorb and retain a lot of heat, and as a result, it is important for thermoregulation. We also talked about our acids, which are the proton donors. Our bases, these are proton acceptors, referred to as alkaline. And buffers, which actually resist any abrupt large swings. Stay tuned. In the next section here, we'll be talking about organic compounds. Organic compounds. And when we talk about these organic compounds, we're talking about kind of like the food you eat, right? The carbohydrates, the lipids, the nucleic acids, and proteins. And ultimately, it is these macromolecules that we consume in dietary, but they also make up you and I, right? Like we use sugar as a fuel, we use lipids as a fuel. We also use it in terms of protection and insulation. Nucleic acids are used to provide energy in terms of adenosine triphosphate, but they also produce proteins as well as other structures of the cell, because they are the DNA and the RNA, the cookbook and the coder. And then the proteins, which is kind of like the workhorse of all this, of all these organic molecules when it relates to the body. They're seen throughout in terms of receptors. They provide structure to cells. They are cell channels as well. So the proteins are really what makes each cell unique and different. But we'll save that talk for another section. Again, thank you for your time. I look forward to your guys' responses and throughout the semester. And take care. Alright, so I recorded that portion there. And I'm going to post that up there on my online lectures. I will finish up with this organic compounds as we talk about the organic compounds, dehydration, synthesis, and hydrolysis. I'm kind of zipping through there. Let me get off of these slides. See if there's nobody's in the chat. Hey, if you're no hating, but if if you guys hopping on, say hi. Have any questions, comments, concerns? Feel free to while you're on the live, hit me up, and I can answer any questions, comments, concerns. But other than that, I'll keep rolling. All right. Let's see here. All right, we still got people. Let's do it. Let's talk about organic compounds. I'm going to pop this up, and then after this, it'll probably be about, I'll publish this on the Canvas page underneath the lectures for chemistry. So this will be published up there. I'll try and make an announcement that this will be This section here is just getting published. I'll clean it up maybe a little bit, and I'm just going to post it right on your Canvas page. So let's see here if I could, on your Canvas underneath your lectures with the YouTube section there. But let's talk about, let me get this, all right. Hello and welcome back to another section of Anatomy and Physiology at Arizona Western College with your professor, Dr. Sean Clavel. And we're going through the sections of chemistry. We talked a little bit about inorganic compounds in the previous section. We're going to talk about organic compounds, particularly those that are important to the human body. We're talking about carbohydrates, lipids, nucleic acids, and proteins. So the things that we consume, and as well as the things that make up us, right? So let me grab my slides and let's get to it. This one. We should first talk a little bit about the way that these organic compounds are either built up or taken apart. Now, particularly these organic compounds, I should give us a little bit of a preface here, have the basic the basic construct of a this idea of a hydrocarbon. A hydrocarbon is a hydrocarbon chain is a chain of carbons, right? You can see here the carbon atoms in a chain here that is then surrounded by hydrogen atoms. And this is kind of the simplest form, as you can see on the top of the slide there, right? The simplest form of an organic molecule. It's called the hydrocarbon. And so there's a large family of these organic molecules that are composed of these hydrogen atoms bonded to a chain of carbon atoms. And sometimes you might see it as like the ball and stick model that looks like this. But ultimately, these organic compounds tend to be what's referred to as polymers. Polymers are like long chains of similar units. So they're built from these smaller building blocks, or what may be referred to as, on the screen here, monomers. And so these monomers, these small building blocks of these larger organic molecules, are synthesized, right? This anabolic process that requires energy. They're synthesized by a term that we call dehydration synthesis. And so in dehydration, actually, let me just, all right. In dehydration synthesis, what we have is the one group or one monomer providing a hydrogen ion, one group providing a hydroxide ion, and as a result, water is removed from the equation, and those monomers create a polymer, which is linked by a covalent bond. And so, as a result, many compounds are soluble in water. Many organic compounds are soluble in water, meaning that if you insert water, so you've got the polymer here of a, let's say it's a carbohydrate, right? Like a simple sugar, you could have glucose, Oh no, come on, let's go. You could have glucose and fructose. Right? And so what happens here is that even that polymer, that disaccharide, there's too big to make it past the cell membrane, and so water acts in a way to break the bond, right? Hydroxide ion is inserted to one monomer, the hydrogen ion to another. That is referred to as hydrolysis. Hydrolysis is the splitting by water. So lysis refers to split, to break, to rupture, as we'll see in a number of different sections throughout the chapter here, throughout the semester here. And so hydrolysis is the splitting by water. And so if you place water in a, if you place a solute like sugar into a solution of water, again, as you can see here, you've got a negative portion that'll attract to one part, a positive portion that'll attract to another. It'll break up that bond. It's called hydrolysis. And so just to kind of backtrack there, right? Dehydration synthesis is the way by which monomers, these small building blocks of organic compounds, are built, and hydrolysis is the way that they're broken down. Keep that in mind. See a star there? Note it. Let's first talk about our first organic molecule, which is the carbohydrate. A carbohydrate, the term carbohydrate itself actually means a hydrated carbon. And so carbohydrates contain carbon, hydrogen, and oxygen, and they do it in this unique ratio. So 1 carbon for every 2 hydrogen for every 1 oxygen. And there can be a number of repeating units of that combination. So carbohydrates are often referred to as saccharides. That's a term that means sugars. And there's going to be 3 types of carbohydrates that we're going to talk about that are important for the body. These monosaccharides, which are actually the monomers, like we've mentioned, right? So those will be seen in our next slide. The disaccharides, which are the 2 sugar units, these made up of 2 monomers. And then the polysaccharides. Polysaccharides are polymers that consist of hundreds or even thousands of monomers. And so in the bottom of our screen here, what we have is, in fact, a ball and stick model of a glucose molecule C6H12. Let me write that up there, right? Because it does follow this 161. So glucose being C6H. Should type it 12. O. 6. That's this right there. That's that ball and stick model. So you can see identifying the carbons here. Nice carbon. It's saturated by all of these hydrogens. And occasionally, there's enough, there's a similar amount of oxygen as there is carbon. So important in terms of the human body, the importance of carbohydrates themselves is they're the primary fuel source for the body. So it's highly regulated in the system. They are used in terms of it's stored in the muscle as well as in the liver. It's in the bloodstream, which is regulated to provide enough nutrients, energy to any of the systems that are needed. So the 5 important monosaccharides here, I'm going to do this in these next slides, include the hexose sugars, so the 6 backbone sugars, and we'll take a look at those in the next slide, and the pentose sugars. So monosaccharides generally contain somewhere from 3 to 7 carbon atoms, and they're used to assemble larger carbohydrates such as the disaccharides and the polysaccharides. These first 3 monosaccharides, the hexose sugars, are actually isomers. It means that they have the same chemical formula but a different structural arrangement. And so the hexose sugars, these C6H12O6, glucose, fructose, and galactose, are really kind of like our dietary sugars, right? Like our dietary sugars, the sugars that we use for energy and that we eat. The pentose sugars are constructs, or how do I put this? The pentose sugars are the sugars that we see in the nucleic acids. They're made in the nucleic acids here. So what we're talking about is the makeup of the monomer of DNA or RNA is a nucleotide, and so the pentose sugar, deoxyribose nucleic acid, the pentose sugar here is the portion of DNA. Then there's a polar phosphate group and a nitrogenous base. So this is what the makeup of DNA is. The single nucleotide is monomer of DNA. And so we see deoxyribose in DNA. And then we see the ribose sugar in RNA. So those 2 pentose sugars are important in the nucleic acids or the nucleotide structure. Disaccharides, or these 2 sugar units, are simple short-chain carbohydrates. There are 3 common disaccharides that we should be familiar with. So the 3 common disaccharides include sucrose. Now, sucrose is a combination of the monomers glucose and fructose. This is a transport form of sugar. It's used by plants and harvested by humans for the use in food. Lactose. Lactose is a combination of glucose and galactose. It's present in milk. And finally, a maltose. Maltose is the 2 glucose units that's present in germinating seeds. So again, the 3 important disaccharides being lactose, sucrose, and maltose. And then the 3 important polysaccharides. So the polysaccharides can be these long or even straight branches of hundreds, maybe even thousands of these sugar monomers. And these polysaccharides are also called complex carbohydrates. So starch is a plant storage form of energy. It's arranged as unbranched coiled chains. As you can see there, the amylose, just a long chain that might be coiled. Or it could be in this amylopectin form, which is, again, this branched form. Glycogen is the animal storage of glucose. or excuse me, of carbohydrates. So these are highly branched chains that are used by animals to store energy in the muscle and the liver. And then finally, the cellulose, which is a long, fibrous form of carbohydrates, which is a polysaccharide, uh, which creates the cell walls and is indigestible by humans. And so, there we review our glucose metabolism. In the next section here, I'll talk about the lipids, followed by proteins and nucleic acids. But we'll take a break here. In the next sections, we'll talk about some of the structures of the other organic compounds, which include, again, the lipids, nucleic acids, and proteins. But again, I want to just share this slide with you here as we can see like the intake. Oh, where'd it go? Just click too fast. The intake of glucose metabolism is starches, glycogen, and disaccharides, as well as some of our monosaccharides, glucose, fructose, and galactose. So we intake all of these. We store it in the form of glycogen, and then it's distributed and utilized in the form of glucose. Glucose is the utilization form. But like I said, in our next section, we'll talk about lipids. We'll take a break now. Thank you, and take care. All right, it's about 7:30. I'm gonna finish this up here. I'm gonna take a break. I'm gonna finish up there and keep everybody in good spirits here as we move through the chapter 2 and 3 here in the semester. Week 3. Thank you guys. It's been a pleasure as always. I will see you next week.